Today we're going to discuss a topic called partial fraction decompositions, and basically what that is it's the reverse procedure for adding fractions. Usually we'll take 1/5 plus a third, get 8/15. Well, in this process we take 8/15 and say what two fractions could get us a sum that would give us 8/15. Likewise, if we have 3x plus 2 over x squared plus x, what two fractions would get us that sum? Now, there's a lot of fractions that would actually do this, but what we're going to look at are proper fractions. In other words, fractions that are reduced in less than 1, and fractions that have factors of 15, basically. So there are about 3 different concepts we're going to cover. The first is if we want to decompose some fraction p over q, where q has non-repeating linear factors of ax plus b. In other words, these factors are linear in nature. No squared terms. P over q's got to be proper, which means it's not greater than 1 or the denominator doesn't go into the numerator. If I split this fraction up, it's going to split up into the sum of a constant a over a specific linear plus another constant a sub 2 over a different linear function for as many factors of q as there are. Looks kind of confusing as we look into general terms, but let's talk about specifics. We're going to decompose the fraction x plus 14 over x squared minus 2x minus 8. And in order to do that, we have to take a look at the factors of x squared minus 2x minus 8, which are x minus 4 and x plus 2. So given that, we can split this fraction up into the sum of 2 fractions with factors x minus 4 and x plus 2, where the constant on top is different. Now, if I want to solve for a and b, what I'll need to do to both sides is multiply by the common denominator, which is that x minus 4 times x plus 2. In doing that, you'll notice the denominator on the left side goes completely. I'm left with x plus 14 is equal to some constant a times x plus 2 plus some constant b times x minus 4. I can distribute this out, giving me x plus 14 equals ax plus 2a plus bx minus 4b. And what I'm going to do next, because I'm trying to solve for a and b, but it seems kind of confusing at this point because I've got 3 different variables going on. So this next step will help us get to this solution. I'm going to group the x terms together. So my x terms are a and b if I were to factor out an x. And then I have constant terms of 2a minus 4b. Now you'll notice that I have an equation. And an equation states that whatever's on one side is equal to another. So what that says is that for my x term on the right side, I have a coefficient with that x term of a plus b. On the left side, my coefficient in front of the x term is 1. So therefore, I can state that 1 is equal to the quantity of a plus b. Likewise, I have a constant term on the left side of 14, and my constants on the right side are 2a minus 4b. So I can say that 14 is equivalent to 2a minus 4b. So you'll notice through this comparison, I've now created a system of equations where I can solve for a and b. To do that, I'd multiply the top set of equations by -2, giving me a -2 is equal to -2a minus 2b. Therefore, I have 12 equaling negative 6b and b equaling negative 2. If b equals negative 2, I know that a has got to equal 3. So therefore, what I can do now is I can take and decompose that fraction. I now know my numerators of the two fractions. We said a was equal to 3 and b was equal to negative 2, so therefore x plus 14 over x squared minus 2x minus 8 is equal to 3 over x minus 4 plus negative 2 over x plus 2. This concept is going to help us quite a bit second semester of calculus. We'll be needing to decompose fractions in order to get our problems started. So in this next problem, we'll just practice one more time. We have 4 over x squared minus 4, and we want to decompose that. So once again, I'll factor the x squared minus 4. And we get x plus 2 and x minus 2. Those are our linear factors, if you will. So therefore, if I have two linear factors as my denominator, then my numerator must be different constant coefficients. I want to solve for a and b, which means I'm going to need to get rid of my denominators. Multiply by x plus 2 and x minus 2 to both sides, as we did in our previous example. Leaving me with 4 is equal to a times x minus 2, and b multiplied by x plus 2. Therefore, 4 would equal ax minus 2a plus bx plus 2b. Group my x terms and my constant terms again, so my x's are multiplied by the sum of a plus b, and my constants are negative 2a plus 2b. And as we did in our previous problem, we looked to see what coefficient is in front of the x term on the left side to relate the a plus b to. Well, I noticed there is no x term on the left side, so therefore the coefficient has to be 0. So 0 would equal a plus b, and 4 then would equal my constant term on the right of negative 2a plus 2b. In this case, I'm going to use a substitution. I can say a equals negative b and substitute in. So I have 4 equals negative 2 times, instead of a, I'm going to say negative b plus 2b. Therefore, I have 4b equaling 4 and b equaling 1. We know that a plus b is equal to 0, so a equals negative 1. And therefore, I can go ahead and decompose this now to negative 1 over x plus 2 plus 1 over x minus 2. So those were a couple examples where I had linear factors of my denominator, and none of those linear factors repeated. If I have a situation where I have a repeating linear factor of ax plus b, then what's going to happen is for every linear factor I have that's repeated, I have to represent that. So notice my denominator here is a linear factor of a sub 1 x plus b1, and then I have its repeated factor here. So this would be like x and x squared if I had those as two different factors of my denominator. So let's go ahead and do an example like that. In this case, we have x minus 1 over, and I have a term that factors. And in this case, it factors to x squared plus 1. Well, x squared is a product of repeated linear factors of x and x. So what I have to do is I have to represent each of those linear factors in my possible decomposition. So what I have is I have a linear factor of x, my repeated factor of x squared, and then my non-repeating factor of x plus 1. Notice I'll have 3 constants in the numerator. Once again, x squared, although it looks like a quadratic, is a repeated linear factor. It's x times x. So now what we're going to do is solve for a, b, and c in this case by multiplying by x squared and x plus 1 to get rid of my denominators. I get x minus 1 is equal to a times x plus 1 plus b times x plus 1 plus c times x squared. Distribute all this out. We get ax squared plus ax followed by bx plus b followed by cx squared. Going to group everything. You'll notice I have x squared terms of a and c, x terms of a plus b, and a constant term of b. When I compare that to my left-hand side of the equation, I notice there are no x squared terms over here, which means the coefficient must be 0. So I know 0 is equal to a plus c. My x coefficient is 1, so 1 must equal a plus b. And in this case, my constant is negative 1, so negative 1 must equal b. Given that, I can go back over to this equation here, and if b is negative 1, I know a is equal to 2. And I know if a is equal to 2, then c must equal negative 2. So I can go ahead and write my decomposition now. I have an a value of 2, so that's 2 over x, plus I have a b value of negative 1, so that's negative 1 over x squared, plus, and then I have a c value of negative 2, so that's negative 2 over x plus 1. If I were to add those up, I would get this quantity here. So now we're going to look at a case where we have non-repeating quadratic factors. Quadratics come in the form of ax squared plus bx plus c. Notice the bx plus c is going to add greatly to this, because if I just have x squared, that's a repeated linear. I have to have the bx plus c in order to have a quadratic. So if I have a quadratic in the denominator, I'm going to have a possible linear in the numerator. And those linears in the numerator could certainly be different. Once again, though, my p over q must be a proper fraction. In other words, the numerator must have a degree smaller than the denominator. So let's do an example. We have this situation where we have 2x squared minus x plus 4 over x times x squared plus 4. Degree on the top is 2, degree on the bottom is 3, proper fraction. I break this apart. I notice this term here is a linear, and this term here is a quad. So when I have a linear as a factor, I have to have a constant over the top of it. When I have a quadratic as a factor, I have to have a linear over the top of it. Since I've already used a as a constant term, I use bx plus c as my representative linear function. I want to solve for a, b, and c, which means I'll multiply by x times x squared plus 4. This is going to give me 2x squared minus x plus 4 is equal to a times x squared plus 4 plus dx plus c multiplied by the quantity of x. Cleaning that up, I get ax squared plus 4a plus bx squared plus cx. grouping these. I group my x squared terms, and I have a plus b. I group my x terms, and I just have c in this case. And I group my constant terms, and I have just 4a. So in this case, I can say that 2 is equal to a plus b. I can say that negative 1 equals c, and I can say that 4 is equal to 4a. So in this case, a is going to equal 1, c is going to equal negative 1, and if a is equal to 1 and a plus b is equal to 2, that means b equals 1 as well. So now I'll go ahead and write my decomposed fraction. My a value is 1 over x. Said we had a b value of 1, so that's 1x minus 1, since c is equal to negative 1 over x squared plus 4. So our last example is where we have a repeated quadratic factor. In other words, we have possibly like x squared plus 2x plus 5 represented twice in our denominator. In that case, we have to represent the initial factor of x squared plus 2x plus 5 and its repeated factor x squared plus 2x plus 5 quantity squared in separate denominators. So I've done that in this problem. We have x squared plus x plus 2 over x squared plus 2 quantity squared. Notice, because I have the c term, this does not qualify as a repeated linear. So once again, my first quadratic term is x squared plus 2. I have a linear over the top of that. And then I have the repeated quadratic function of x squared plus 2 quantity squared. And I need a new linear over that. I've already used ax plus b, so now I use cx plus d. Multiplying both sides by this quadratic squared, I get x squared plus x plus 2 equals ax plus b multiplied by x squared plus 2 plus cx plus d. I'll have to FOIL this out now, giving me ax cubed plus 2ax plus bx squared plus 2b plus cx plus b. Let's go ahead and group everything now. Here's ax cubed. Got some squared terms. There's only one of them, that's the b. I have some x terms. In this case, I have 2a and c. And then I have constant terms of 2b and b, which is 3b for my constant terms. And that's going to be equivalent to x squared plus x plus 2. Now, in this case, I am looking for a cubed coefficient, and there are no cubes, which means since the cube only represents the coefficient of a must equal 0. b is corresponding to my coefficient in front of the x squared, so b is equal to 1. I know that 2a plus c is equal to the coefficient in front of x, so 1 is equal to 2a plus c. So in this case, since a was equal to 0, c's got to equal 1. And we know b's already equal to 1. So I'm pretty much done in this case. Whoops. Let's go back. I just noticed I made a mistake. This is cx plus d. So this is d. Sorry about this, guys. So in this case, I have 2b plus d as my constant term. So my constant term in this case is 2. and that's equal to 2b plus d. Sorry about that. I know b is equal to 1, so therefore if b is equal to 1, d has to also equal 0. Now I can go ahead and write my decomposed fraction. I have an a value of 0, so there's no x term, just a b term of 1 over x squared plus 2. My c term is 1, so I have an x. My d term is 0 over x squared plus 2 quantity squared. So there are all four situations you might have of linear, repeated linear, quadratic, and repeated quadratic factors of denominators in an initial fraction which we want to decompose. Write your lesson summary, do your My Math Lab, and we'll do some examples tomorrow.